The reactions of carboxylic acid derivatives are very important for biology and especially for enzymes. So there's a class of enzymes called serine proteases, and these ones take things like esters, for example, and convert them into carboxylic acids. Though we were very worried when we were dealing with our carboxylic acid derivatives in terms of whether we are in acidic, basic, or neutral conditions. With the enzymes, they give their own conditions, and everything in the enzyme is set up to specifically do this reaction. And so they're going to have protons in the right places to help stabilize negative charges that generate. So, for example, when our carboxylic acid comes to orient itself into the active site, which is represented by this kind of very shortened representation with some of the key amino acids that are going to be players in that proton transfer, those proton transfer steps, for example, and the reaction itself. We also have this one part of the enzyme active site that actually contains a group capable of stabilizing this negative charge when it develops. So right now, what it's doing is it's activating the carbonyl for attack by participating in hydrogen bonding with the oxygen of the carbonyl carbon. And so that would be like having a strong acid. That delta plus is going to be pretty strong on that carbon of the carbonyl. So that delta plus is going to get stronger because of those interactions. What's going to happen for the nucleophilic attack is we're going to have a series of proton transfers to get the attack to get that molecule onto the enzyme itself. And then our nucleophile is going to come and attack. So the water is our nucleophile in this case. The serine protease is like a designer acid or base kind of thing. And so to draw our mechanism, we start off from the far left where we can push all of these arrows to show the nucleophilic attack. So starting off from that negatively charged oxygen, we do the series of proton transfers basically to make the oxygen of the serine nucleophilic enough to go and attack. That's why it's called a serine protease, because the serine amino acids residue is the OH group. It's an alcohol group, and it's going to go and be our nucleophile, our first nucleophile anyways. And so that's going to allow us to get this tetrahedral intermediate. So this one also goes by tetrahedral intermediate. So we're going to have our R group, our O minus, which is going to be stabilized by those H's. So it's still H bonding with those. And then we're still going to have our OR group attached to the molecule. So this is our tetrahedral intermediate. And our other residues are all kind of going to have this one's going to have a H. The H, that's that one there. That's H. This one is going to have, this nitrogen's going to have the H from there. So that shows up there. And then our oxygen is going to be bound to that carbon. And again, these are stabilizing the negative charge. Now what's going to happen, we need to basically get this group into the OH. So we need to get this off of the molecule. So we're going to have a collapse of the tetrahedral intermediate. So we formed it, we're going to collapse it. That collapse is going to happen in exactly that reverse way of how the addition happened. And so what we're going to do, we're going to start at the oxygen, bring the electrons down. That leaving group's going to leave, and it's going to go pick up an H that's not very far away. So this H right here is a great one for it to pick up so that it becomes nice and neutral upon leaving. We're going to have those electrons shuffle back to regenerate that active site pretty much with respect to these two the way they were originally. The serine is still going to be attached to our derivative, so we're going to show that in the next slide. So now we have the first two residues back the same way that they were. We have our, now our molecule is actually covalently bound to the active site of the enzyme. And now this oxygen still being stabilized by hydrogen bonding to those two groups there. we have our nucleophile come in. So water can come into that active site and it's going to be able to attack. It's going to be activated for attack. So it's almost like this mechanism is happening under acidic and basic conditions at the same time. That is how well set up this active site is. So what's going to happen? We want the nucleophile to be activated. So we're actually going to do a deprotonation of the nucleophile, and that's going to go and attack like we have a negatively charged nucleophile doing the attack. And so what's going to happen in terms of arrow pushing, we're going to start that same cascade that we were doing, only this time instead of using that bond to go grab the electrons from the H of the serine, we're going to use this bond to go grab the H from the OH because that's our nucleophile now. And then we're going to have the OH go in and attack and then make another tetrahedral intermediate. And so now we're going to still have our R group, our negatively charged oxygen, and now our new bond to our OH. And it's just an OH because we already removed that hydrogen, and now that hydrogen is over here. And our R group is down here. So, and again, that negative charge is being stabilized by the hydrogen bonding to those groups there. And so now we're going to do another collapse because we do need to get that product where we're basically, our goal now is to take this molecule off of the enzyme active site. It can't stay there forever. And so we're going to, in this next step, collapse that tetrahedral intermediate to kick it off of the active site and get our carboxylic acid. And so to do that, we can draw our arrows starting at the oxygen that's negatively charged again. We're going to go back in this opposite direction, do that second cascade that we showed. That's going to regenerate the active site just the way it was before our molecule came in the first place. And that's what enzymes do. They're catalysts. So they help out this reaction by attaching to this molecule. They did the reaction they needed to do, and then they release the molecule, and then they're ready to take in another molecule to do the same thing. And so they get regenerated just like a catalyst in a reaction. And that's going to allow us to make our carboxylic acid. That's going to kind of float away. Then another molecule of the ester can come in and another molecule of water. We can do the same thing all over again. So that's kind of, we get that active site right back to how it was when we first started off. And that's what enzymes do. So we focused a lot on acidic, neutral, basic conditions. Enzymes are kind of their own conditions. They set up everything perfectly. They activate the electrophile. In our case, we were activating the electrophile by the hydrogen bonding with this group here. They activate the nucleophile by deprotonating. So that first step, this was the nucleophile, and we deprotonated it, and then right away it went to attack. So we've also activated the nucleophile. When we had water, did the same thing. This group went to deprotonate the water, and the OH minus basically was what went and attacked. And so we're actually kind of maximizing on both. In the actual lab, we can't really do this with just adding a strong acid and a strong base. We can't add those both in, or else they'll just react together and we won't get the reaction we want. But in the enzyme active site, everything is positioned specifically in order to do this reaction as best as possible. We can only hope to get as close as we can in the lab, but in the enzyme active site, everything happens perfectly.